Hey, today we are in Chapter 5, Applications of Derivatives. We are in Section 5.2, Mean Value Theorem, or MVT. In this section, you will learn specifically about what the mean value theorem is. We'll talk about physical interpretation of it, increasing and decreasing functions, and other consequences of our mean value theorem. So the mean value theorem for derivatives. If y equals f of x is continuous at every point of the closed interval, so again, continuous and closed, and differentiable at every interior point, there is at least one point in the interior with which f prime of c equals f of b minus f of a over b minus a. So down here you can see what I wrote. There is a point in the inside where our instantaneous velocity is equal to the overall average velocity. That's what the mean value theorem says. In order for this to hold true, it needs to be continuous, closed, and differentiable. So it has to have those three parts. If it doesn't have those three parts, any of those three parts, then mean value theorem won't exist. Does it mean that this can't be true? It just means that we're not guaranteed to have that value. Okay, so example, we're exploring the mean value theorem. So show that the function f of x equals x squared satisfies that hypothesis of the mean value theorem on the interval 0 to 2. Then find a solution C to the equation f prime of c equals f of b minus f of a over b minus a on this interval. So we are starting. The function f of x is equal to x squared, of course. That is continuous from 0 to 2, okay? You can see over here we have a graph. It's continuous. And it's also differentiable. So I can find the derivative, and all the values of the derivative between 0 and 2 are going to work as well. So since f of 0 equals 0 and f of 2 equals 4, and we can find the slope of this, okay, so this is where they got this, and they set it equal to the instantaneous velocity equation. So the instantaneous velocity is 2x. So we're finding a c value. Instead of x, they just put c in there. And they are solving. So where does 2c equal 2? That's where c equals 1. So the value, and you can again just leave it as x. I usually end up leaving it just as x. So at 1, this slope, the instantaneous slope at x equals 1, is going to equal to the average slope from 0 to 2. Increasing function, decreasing function. Let f be a function defined on the interval I, and let x of 1 and x of 2 be any 2 points on the interval. F increases on the interval if x of 1 is less than x of 2. So meaning this value is going to be less than this value. And same thing here, we're holding that true in the opposite way. Corollary, increasing and decreasing functions. So it just says let f be continuous on a closed interval a to b and differentiable on the open interval a to b. If the derivative is greater than 0, if your derivative is positive at every point on the graph, f is increasing on a to b. If f prime is less than 0, or if our derivative is negative at each point, then f is decreasing. And this is something we've already talked about, and we've talked about it in terms of graphs, but now we're doing it in terms of words so we can make sense of those values. So example, determining where graphs rise or fall. So where is the function f of x equals x cubed, 2x cubed minus 12x increasing, and where is it decreasing? Well, we just talked on the last page. Your function is going to be increasing when your derivative is greater than 0, and it's going to be decreasing when the derivative is less than 0. So we just do this first one. find the derivative, set it greater than 0, and find those values. So here's the derivative. We set it greater than 0, and it will be above 0, either less than negative square root of 2 or greater than positive square root of 2. And that's for increasing. And then we're going to do a likewise one for decreasing. Your f prime is going to be negative, and we solve, and it's basically outside of these values, it's increasing. Inside of these values, it's decreasing. Functions with the derivative equal to 0 are constant. So it just means that at any point on the interval, there's a constant c for which f of x equals c if f prime of x equals 0 at every point. So it's basically, it has a horizontal slope. It's called the constant line. Functions with the same derivative differ by a constant. So if they get the same derivative, they have this constant up and down that can give you the same value. So example, let's say we have x squared plus 2, and that's our f of x. And then we can have g of x equals x squared plus 5. Sorry, cursor, not so great with my mouse. So I have x squared plus 5. When I find the derivative of f of x, I just get 2x. And when I find the derivative of g of x, I also just get 2x. So what this says, if we look back at it, it's your derivatives are equal at each point on the interval. There is a constant c such that they are away from each other by that c value. These are away from each other by 3. Antiderivative. So a function f is an antiderivative of a function f of x. So notice that this guy is capital and this is lowercase. So they will denote, excuse me, capital F of x as the antiderivative and lowercase f of x is your original. So if f prime of x equals f of x for all x in the domain of f. It's the process of finding an antiderivative is called antidifferentiation because of course we need another really long word. So finding velocity and position given some information. So find velocity and position functions of a freely falling body for the following positions, following set of conditions. So the acceleration is 9.8 meters per second squared and the body falls from rest. Assume that the body is released at time equals 0. So that means that our acceleration is 9.8 because that's what it told us, and v sub 0 equals 0. So we are going to write our derivative. So we're working backwards. If this is the acceleration, our velocity has to be 9.8t plus some c value that we don't know, and we just learned it's that c value on the last page. Well, I know v of 0 equals 0, so I'm going to put 0 in for t and for v, and I'm going to solve for c. Well, you guys, as you plug through, should see that c is going to be equal to 0. So here is my velocity equation. Woohoo! Then we need to find our position. We know that v of t equals 9.8t. We just found it. And s sub 0 equals 0. So working backwards to figure out what your position equation is, I would, if you think about it, we're doing derivative. We need the power rule. So we would drop the exponent down, subtract 1. Right now our exponent here is a 1. So our exponent would have been a 2. So I'm going to bring the 2 back up and divide this value by 2. We have the plus c. Again, we're filling 0 in for s and for 0 and finding our z or c value. So here is our position. And again, there is our velocity equation. We're finding all the antiderivatives. So we are going to work on this in class. We are also going to find it through a specific value, and then we'll do a few more problems in class. So hope that was good. I will talk to you soon.